this H looks like near the critical points, perhaps with some nice set of coordinates, not H as presented. So I might want to change Z to Z, X to X plus Y by 2 and so on and so forth, or maybe even more complicated transformation. So that my H around these critical points has a certain standard form. And you see what standard form and so that's and the height function is simply Z. Okay? And I don't know how to solve for Z because here remember this by definition is X, Y, Z. This one again now let's practice form. So this is what it is. Right? So what is our H on Z is just Z. I want to understand Z around, let's say this one. You can do the rest by symmetry. So what is this? This is going to be this point, right? I'm choosing a plus because I'm trying to solve it around the North Pole. If you wanted to solve it around the South Pole, you can know because Z takes another minus 1. That sounds interesting. Right? Yes. Oh, acha, yes, yes, sure. Yes, okay. So what I want to do is I want to expand this, which I can, because you see near the North Pole, x square plus y square is very small. Because near the North Pole, Z is essentially close to 1. It's a very small thing. If I expand, what do I get? I want you know this. So I just put this like this. X square plus y square. The next term is going to be the square of this divided by some appropriate factor, and then the cube of this divided by some appropriate factor. 4 because it's the square of this with a factor, the cube of this with a factor, and so on. Now, what I'm suggesting is you can replace your x and y with two variables x tilde, y tilde, which are coordinate transformations from the xy coordinate system to x tilde, y tilde, such that what is my name? My name is so question mark 1 minus. I'm claiming that in a sufficiently small disk, something like this, sufficiently small disk around the North Pole, I can have a change of coordinates. So instead of x, y, I can have a x tilde, y tilde, which are both functions of x, y and the invertible functions. So that this in the x tilde, y tilde coordinate system looks like 1 minus x tilde squared minus y tilde squared. So how do you do this? If you remember this is x squared plus y squared divided by some. There's a minus, okay. And then so on. So let's create. So what you could do is you could simply take x squared plus y squared by 2. If you take this common, you have 1 minus, you get 5 something like 2. Okay. The key point is that you can choose x, y to be sufficiently small so that this thing converges. This is the dominating term. So what I propose is x tilde is going to be x over square root of 2 square root of alpha. And y tilde is y. So I'm saying if you choose this change of coordinate, you have to check that this will be a change of coordinate 5 or something, and you can solve for this in terms of the other. But if you let these your new x tilde, y tilde coordinate, then this entire thing becomes x tilde squared plus 5 tilde, just by construction. Okay. So this allows me to write this as or if you want to let me write it this way. I want to have 2 minuses. You will see why I want 2 minuses. So I'm saying this is simpler expansion, this is the dominating term, you can absorb the truth and you can absorb everything. This is what it looks like. Yeah, but so I'm not saying this is a linear change at all. So there's a field which maps just to this when the T is locally equal at 0. So I mean, yeah, none of these are going to be linear change of coordinates for this. Yeah. Okay, so yes, yes. So okay, so if you want to claim that x tilde as a function of xy and y tilde as a function of xy, is a valid change of coordinates means that of course it sends 0, 0 to 0, 0, but then you check the derivative of x tilde y tilde at the origin. So inverted inverse function tells you there's a local inverse, possibly a little smaller. Right? So that will guarantee that this is solve for x in terms of x tilde y tilde and vice versa, perhaps in an even smaller case, or a smaller open. Here it takes us in. So when I say a valid change of coordinates, it's not like you write something in terms of the old one and you cannot get them back. So both have to be smoothly expressible in terms of the usual way you check that is inverse function. So yeah, it's a non-linear change of coordinates because alpha, as it was pointed out, involves x. Right. So what is the point of writing it in this form? The point of writing it in this form is I'm going to now compute the Hessian of this in the x tilde y tilde form. Because I have a nice coordinate system, I don't have to deal with all these s. So if I compute that, what happens? So I compute the Hessian of h at 0, 0, 1 in terms of the x tilde. So what does that mean? Well, we have to differentiate del qf by del x tilde del y tilde. That's a fixed term. Del qf by del x tilde del x tilde, well, that's this, and that's this. Right? So we're good. Just get that. I get a minus because there already is a minus. Minus is tag term. Okay. So this, as you see, is look at how this acts. As it turns out, the index is essentially going to be, if you take this symmetric bilinear form to diagonalize this, it's invertible, so there are no zeros on the diagonal. You just pick up the number of minus signs, that's your index, and the number of positive signs, that's your true index. So in general, there will be a nullity because Silverstone theorem says that you have some pluses, some zeros, and some minuses. The fact that this is, as it turns out, this is an invertible matrix. So this has no nullity and both the eigenvalues are minus. But sometimes you have two minuses, one positive, but this Morse condition guarantees that the Hessian when you diagonalize will have no zeros on the diagonal. Okay, so keep this thing in mind. If we did the same thing for the south pole, what would have changed? So you will have a minus here, right? You have a minus here, minus here. This becomes a plus, this becomes a plus, right? So to do the same thing, exact same thing, with the obvious change of sign, you have the same x become similar one. They're both pluses. So here, if you're counting the number of negative eigenvalues, there's nothing. 0. So that's 0 that you see. And one of the things you prove is that these things which are invariant of the bilinear form, of course, doesn't depend on which coordinate system you compute. So you compute it in a system which is computing all the coordinates. But that requires you to go to some equals function theorem. Okay. I think this is more interesting. You see why these ones are. Okay. Any questions? Good. Oh, the maybe okay. Yeah, you're right. So you could have computed the Hessian with this because you have to plug in 0, 0. I wanted it to be of this form because I want, when I write the Morse lemma, I'll not prove the Morse lemma, but hopefully this will be something absolved. Yes. Right. Yeah, you can make this thing itself, but I wanted this form because you soon see a lemma which says there always exists 5 coordinates coordinate system. Then clean up all the higher terms and okay, so let's put this example. I'm not sort of like characters to change the way I oriented the torus in my notes. I'm going to pretend that this is the x-axis and the torus sits, like how a swimming tube sits on the floor. So I don't have to change all the coordinates again. So this is my height function. I have to this is my torus. You can imagine this